Hi there. It's another edition of Luja's Little Lessons. Today's topic is logic. In geometry, we are constantly drawing conclusions from information that we know. Inductive and deductive reasoning are two fundamental forms of reasoning for mathematicians. The formal theorems and proofs that we rely on today all began with these two types of reasonings. Even today, mathematicians are actively using these two types of reasonings to discover new mathematical theorems and proofs. Believe it or not, you yourself might be using inductive and deductive reasoning when you make assumptions about how the world works.
First, let's discuss inductive reasoning. Inductive reasoning is reaching a conclusion based off a series of observations. A conclusion that is reached by inductive reasoning may or may not be valid. Let's take this for example. Let's say you notice that all the mice around you are brown, and so you make the conclusion that all mice in the world are brown. Can you say this is a certain conclusion is correct? No, because it is based off a few observations. This is an example of inductive reasoning and the beginning of forming a correct conclusion or correct proof. What this observation has given you is a starting point or hypothesis to test out. Let's watch this next example of inductive reasoning.
You and 9 other individuals have been captured by super-intelligent alien overlords. The aliens think humans look quite tasty, but their civilization forbids eating highly logical and cooperative beings. Unfortunately, they're not sure whether you qualify, so they decide to give you all a test. Through its universal translator, the alien guarding you tells you the following. You will be placed in a single file line facing forward in size order, so that each of you can see everyone lined up ahead of you. You will not be able to look behind you or step out of line. Each of you will have either a black or a white hat on your head, assigned randomly, and I won't tell you how many of each color there are. When I say to begin, each of you must guess the color of your hat, starting with the person in the back and moving up the line. And don't even try saying words other than black or white, or signaling some other way, like intonation or volume. You'll all be eaten immediately. If at least 9 of you guess correctly, you'll all be spared.
You have 5 minutes to discuss and come up with a plan, and then I'll line you up, assign your hats, and we'll begin.
Can you think of a strategy guaranteed to save everyone? The key is that the person at the back of the line who can see everyone else's hats can use the words black or white to communicate some coded information. So what meaning can be assigned to those words that will allow everyone else to deduce their hat colors? It can't be the total number of black or white hats. There are more than 2 possible values. But what does have 2 possible values is that number's parity. That is, whether it's odd or even. So the solution is to agree that whoever goes first will, for example, say black if he sees an odd number of black hats, and white if he sees an even number of black hats. Let's see how it would play out if the hats were distributed like this. The tallest captive sees 3 black hats in front of him, so he says black, telling everyone else he sees an odd number of black hats. He gets his own hat color wrong, but that's okay, since you're collectively allowed to have one wrong answer. Prisoner 2 also sees an odd number of black hats, so she knows hers is white and answers correctly. Prisoner 3 sees an even number of black hats, so he knows that his must be one of the black hats the first 2 prisoners saw. Prisoner 4 hears that and knows that she should be looking for an even number of black hats, since one was behind her. But she only sees one, so she deduces that her hat is also black. Prisoners 5 through 9 are each looking for an odd number of black hats, which they see, so they figure out that their hats are white. Now it all comes down to you at the front of the line. If the 9th prisoner saw an odd number of black hats, that can only mean one thing. You'll find that this strategy works for any possible arrangement of the hats. The first prisoner has a 50% chance of giving a wrong answer about his own hat, but the parody information he conveys allows everyone else to guess theirs with absolute certainty. Each begins by expecting to see an odd or even number of hats of the specified color. If what they count doesn't match, that means their own hat is that color. And every time this happens, the next person in line will switch the parody they expect to see. So that's it. You're free to go. It looks like these aliens will have to go hungry, or find some less logical organisms to abduct.
The prisoners and hats puzzles is a classic logic problem with many variants. Like other puzzles where each player has information about the other players, but not about themselves, they rely on inductive logic to figure out the other player's thought processes to work out the missing information.
Now let's take a look at deductive reasoning. Deductive reasoning is the process of reaching conclusions based on previously known facts. The conclusions reached by this type of reasoning are valid and can be relied on. For example, you know for a fact that all pennies are copper-colored. Now, if your friends gave you a penny, what could you conclude about this penny? Can you conclude that all pennies will be copper-colored? Yes, you can say this for certain because your statement is based on facts. This is an example of deductive reasoning. Now let's try an example that's a little more involved.
Before he turned physics upside down, a young Albert Einstein supposedly showed off his genius by devising a complex riddle involving this list of clues. Can you resist tackling a brain teaser written by one of the smartest people in history? Let's give it a shot. The world's rarest fish has been stolen from the city aquarium. The police have followed the scent to a street with 5 identical-looking houses. But they can't search all the houses at once, and if they pick the wrong one, the thief will know they're on his trail. It's up to you, the city's best detective, to solve the case. When you arrive on the scene, the police tell you what they know. 1. Each house's owner is of a different nationality, drinks a different beverage, and smokes a different type of cigar. 2. Each house's interior walls are painted a different color. 3. Each house contains a different animal, one of which is the fish. After a few hours of expert sleuthing, you gather some clues. It may look like a lot of information, but there's a clear logical path to the solution. Solving the puzzle will be a lot like Sudoku, so you may find it helpful to organize your information in a grid, like this. To start, you fill in the information from clues 8 and 9. Immediately, you also realize that since the Norwegian is at the end of the street, there's only one house next to him, which must be the one with blue walls in clue 14. Clue 5 says the green-walled house's owner drinks coffee. It can't be the center house, since you already know its owner drinks milk. But it also can't be the second house, which you know has blue walls. And since clue 4 says the green-walled house must be directly to the left of the white-walled one, it can't be the first or fifth house either. The only place left for the green-walled house with the coffee drinker is the 4th spot, meaning the white-walled house is the 5th. Clue 1 gives you a nationality and a color. Since the only column missing both these values is the center one, this must be the Brits' red-walled home. Now that the only unassigned wall color is yellow, this must be applied to the first house, where clue 7 says the Dunhill smoker lives. And clue 11 tells you that the owner of the horse is next door, which can only be the second house. The next step is to figure out what the Norwegian in the first house drinks. It can't be tea. Clue 3 tells you that's the Dane. As per clue 12, it can't be root beer since that person smokes Blue Master. And since you already assigned milk and coffee, it must be water. From clue 15, you know that the Norwegian's neighbor, who can only be in the second house, smokes blends. Now that the only spot in the grid without a cigar and a drink is in the 5th column, that must be the home of the person in clue 12. And since this leaves only the second house without a drink, the tea-drinking Dane must live there. The fourth house is now the only one missing a nationality and a cigar brand, so the Prince-smoking German from clue 13 must live there. Through elimination, you can conclude that the Brit smokes Pall Mall and the Swede lives in the fifth house, while clue 6 and clue 2 tell you that these two have a bird and a dog, respectively. Clue 10 tells you that the cat owner lives next to the blend-smoking Dane, putting him in the first house. Now, with only one spot left on the grid, you know that the German in the green-walled house must be the culprit. You and the police burst into the house, catching the thief fish-handed. While that explanation was straightforward, solving puzzles like this often involves false starts and dead ends. Part of the trick is to use the process of elimination and lots of trial and error to hone in on the right pieces. And the more logic puzzles you solve, the better your intuition will be for when and where there's enough information to make your deductions. And did young Einstein really write this puzzle? Probably not. There's no evidence he did, and some of the brands mentioned are too recent. But the logic here is not so different from what you'd use to solve equations with multiple variables, even those describing the nature of the universe.
Einstein's puzzle is a classic deductive reasoning puzzle. We started with concrete facts and used this information to deduce factual conclusions. In geometry, we will use both inductive and deductive reasoning. We will start with inductive reasoning to draw some general conclusions and then use deductive reasoning from there to assemble our facts. Now let's get started and write some proofs.